Welcome to an exploration of how bending and curving nanomaterials creates extraordinary electronic and magnetic effects that simply don't exist in bulk materials. At the nanoscale, when materials bend or curve, their atomic arrangement changes in ways that fundamentally alter electronic and magnetic properties. Why does bending matter so much at the nanoscale? In bulk materials, if you bend a metal sheet, you might change its shape, but the electronic properties remain essentially unchanged. However, at the nanoscale, the surface-to-volume ratio becomes enormous, and every atom matters. The transition from bulk to nanoscale represents a fundamental change in how materials respond to mechanical deformation. The surface-to-volume ratio is inversely proportional to the radius, meaning smaller structures have exponentially more surface influence. Let's understand the fundamental physics of strain at the nanoscale. Strain measures how much a material deforms relative to its original size. Strain epsilon equals the change in length divided by the original length. This dimensionless quantity captures the extent of deformation. When we bend a nanomaterial, the outer surface experiences tensile strain, while the inner surface experiences compressive strain. For a structure bent into a curve with radius r, we can calculate the strain distribution. The strain at distance y from the neutral axis equals y divided by r, the radius of curvature. Let's consider a practical example with a carbon nanotube. For a carbon nanotube with radius of curvature 5 nanometers and diameter 1 nanometer, the maximum strain is 0.5 nanometers divided by 5 nanometers, giving 10% strain. This is enormous. You might ask, why is 10% strain so significant? The answer is that most bulk materials fracture at only 1 to 2% strain, but nanomaterials can sustain much higher strains due to fewer defects. Now let's explore how strain modifies the electronic band structure. When you strain a material, you change the distance between atoms, which directly affects how their electron orbitals overlap. In the unstrained lattice, atoms are evenly spaced. Under strain, this spacing increases, weakening orbital overlap and modifying electronic properties. We can quantify this energy shift using deformation potential theory. The energy shift delta E equals the deformation potential G times the strain epsilon. For graphene, the deformation potential is approximately 20 electron volts, which is quite large. With 10% strain, the energy shift is 20 electron volts times 0.1, giving 2 electron volts. This is huge compared to thermal energy. For comparison, thermal energy at room temperature is only 0.026 electron volts, so our 2 electron volt shift dominates all thermal effects. In an unstrained semiconductor, the conduction and valence bands are separated by a fixed band gap energy. Under strain, both bands shift and the band gap increases by delta E, fundamentally changing the material's optical and electronic properties. One fascinating effect is flexoelectricity, where bending creates electrical polarization. Even in materials that normally have no piezoelectric effect, a strain gradient from bending can break the symmetry and induce polarization. The polarization P sub I equals the flexoelectric coefficient mu times the gradient of strain, capturing how curvature creates electric fields. When a nanomaterial bends, a polarization field develops perpendicular to the surface, creating an effective electric field. Let's calculate the magnitude of this flexoelectric field. The flexoelectric coefficient is typically around 10 to the minus 10 coulombs per meter. The strain gradient for our bent nanotube is 0.1 divided by 5 nanometers, giving 2 times 10 to the 7th per meter. The resulting polarization is approximately 2 times 10 to the minus 3 coulombs per square meter. The electric field equals P divided by epsilon 0, giving approximately 200 million volts per meter. This is an enormous field. Curvature also dramatically affects magnetic properties through magnetoelastic coupling. The preferred direction of magnetic moments depends critically on how atoms are coordinated with their neighbors. On a flat surface, a magnetic atom with six-fold coordination has its magnetic moment pointing perpendicular to the surface. On a curved surface, the coordination is distorted, causing the magnetic moment to tilt, fundamentally changing magnetic anisotropy. We can quantify this energy change using magnetoelastic theory. The magnetic energy change equals the magnetoelastic coupling constant B 1 times the strain. For cobalt nanostructures, B1 is approximately 5 megajoules per cubic meter. With 10% strain, the energy change is 500 kilojoules per cubic meter, enough to completely reorient magnetic domains. How does this magnetic energy compare to thermal fluctuations? For a 5 nanometer nanoparticle, this strain-induced magnetic energy dominates thermal fluctuations above 100 Kelvin, allowing strain-controlled magnetism at room temperature. The interplay between quantum confinement and mechanical strain creates unique phenomena. In quantum dots, electrons occupy discrete energy levels due to quantum confinement. The energy of level n equals h bar squared pi squared n squared divided by 2 times the effective mass times the confinement length squared. In a quantum dot, electrons occupy discrete energy levels like rungs on a ladder. When we apply strain, we change the physical size of the quantum dot. The length becomes L times 1 plus epsilon, where epsilon is the strain. The energy levels then scale as 1 over 1 plus epsilon squared, creating a strong strain dependence. For a typical 10% strain, the fractional energy change is 1 minus 1 over 1.1 squared, giving approximately minus 17%. The energy levels drop significantly. This huge energy shift enables strain-tunable quantum dots, where mechanical deformation controls optical emission wavelength. Curvature also fundamentally alters lattice vibrations and thermal properties. In flat crystals, phonons follow well-defined dispersion relations. The frequency squared equals 4 times the spring constant c divided by mass m times sine squared of Ka over 2. This creates the characteristic phonon dispersion curve, showing how frequency depends on wave vector. When we curve the material, the force constants between atoms become position-dependent due to strain. The force constant at position r equals C0 times 1 minus beta times y over r, where beta quantifies strain-phonon coupling. This spatial variation causes phonons to preferentially propagate in certain directions, creating thermal conductivity that depends strongly on direction. Let's consider a silicon nanowire as a concrete example. For a radius of curvature of 10 nanometers and beta approximately 3, the force constant variation from inner to outer surface is 150%. This completely changes phonon transport. Experimental measurements show thermal conductivity can drop by a factor of 10 in highly curved nanowires compared to straight ones. Curvature dramatically enhances spin-orbit coupling, enabling new spintronic phenomena. Spin-orbit coupling occurs when an electron moving through an electric field experiences an effective magnetic field in its rest frame. The spin-orbit Hamiltonian contains the gradient of potential crossed with momentum, dotted with the Pauli matrices, capturing how orbital motion couples to spin. In curved nanostructures, the broken symmetry and strong electric fields from strain dramatically amplify spin-orbit effects. This creates a spin texture where spin orientation varies systematically along the curved surface, enabling spin manipulation without magnetic fields. In carbon nanotubes, curvature-enhanced spin-orbit coupling can be 100 times stronger than in flat graphene. The curved spin-orbit coupling scales as the flat value times A over R squared, where A is the lattice constant. For a 2 nanometer radius nanotube, this gives 0.16 millielectron volts, enabling spin manipulation at accessible temperatures. These curvature effects enable revolutionary technologies. These effects enable flexible electronics, ultra-sensitive strain sensors, tunable optics, and nanoscale actuators. Strain sensors based on these effects achieve gauge factors exceeding 1,000, far superior to conventional metal strain gauges with factors of 2 to 5. Why do nanoscale strain sensors achieve such extraordinary sensitivity? The answer lies in quantum tunneling. The tunneling current between nanostructures depends exponentially on their separation, creating enormous sensitivity to tiny mechanical changes. Current is proportional to exponential of -2 kappa d, where d is the gap and kappa is inverse decay length. The relative current change per unit strain equals 2 kappa L, easily reaching 1,000 for nanoscale gaps. Despite tremendous potential, significant challenges remain. Key challenges include reproducible fabrication of curved nanostructures, ensuring long-term mechanical stability, and scaling up to practical devices. Mechanical fatigue becomes critical when nanostructures undergo repeated high-strain cycles, potentially limiting device lifetime. The number of cycles to failure scales as strain to the power minus alpha, where alpha is approximately 6, meaning small strain increases dramatically reduced lifetime. How can we overcome these fatigue limitations? Emerging solutions include self-healing nanomaterials that can repair defects and protective coatings that reduce surface degradation while maintaining flexibility. Looking forward, controlled strain engineering could enable programmable matter, where material properties are dynamically tuned by mechanical deformation. Let's summarize the key insights from our exploration. 6 fundamental insights connect curvature to nanoscale properties. First, nanomaterials sustain strains up to 10%, far beyond bulk material limits due to reduced defect density. Second, these strains shift electronic band gaps by electron-volt scales, completely transforming electrical and optical properties. Third, flexoelectricity generates electric fields approaching 100 megavolts per meter through pure mechanical deformation. Fourth, magnetic anisotropy and moment orientation change dramatically in curved geometries, enabling strain-controlled magnetism. Fifth, quantum confinement energies shift by 17% for 10% strain, creating tunable quantum states. Sixth, spin-orbit coupling can enhance 100-fold in curved nanostructures, enabling new spintronic functionalities. What does all this mean for the future of nanotechnology? 6 insights connect curvature to nanoscale properties, opening doors to unprecedented control over quantum phenomena.